So welcome everyone. This is our fourth and last session of the OOMMF tutorial. It will take about 2 hours. Thank you for coming. As a reminder, if you haven't been here before, so if you have a question, please pick one of the people who are listed as moderators in the participants panel. This is me, Shin Fan, and Donald Porter, and send a private message through chat to one of us. So pay attention to the icon with the thumbs up next to the name. That means a moderator is ready to take questions. And pick one at random, so you don't send all questions to just one of us. And those questions will be communicated to Dr. Donahue, who will answer directly relevant questions during the session, and then other questions will be taken over either to the end of the session or to NanoHub. And you can also always ask questions on NanoHub. So if you're watching on Twitch, you can use the chat box to ask questions too. You need to be a registered Twitch user for that. It's free. You can register an account if you don't have one. So with this, let's turn it over to Dr. Donahue and start with the last session. Please go ahead.
Hello, thank you. So again, thank you to the Spintronics seminar, Professor Fan and Professor Belashenko. Also NanoHub support, Tanya Fulton's, IEEE Magnetic Society for sponsoring these talks. A disclaimer at NIST, any products that I mention are for identification purposes only. They do not, does not represent endorsement by NIST. Okay, so where are we? So this is the fourth one. We're going to be talking a little bit full on from last week about setting up some advanced simulations, but mostly I want to talk about post-processing today. And I'll touch on the homework first off. Okay, I put slides up that go along with this material. The pages, the files are mentioned on the pages. You can get the slides and the files, the sample files, from the OOMMF site on the tutorial page. These slides are already up there, by the way, if you want to download those. Okay, so to recap, so last week the homework was to take the output. So the first, session 2 homework was to take a strip of material that had perpendicular anisotropy and DMI, has skyrmion in it, and relax into a equilibrium configuration where you needed to introduce some pinning, a pinning site to hold the skyrmion in place. Last week's homework was then to apply a current, a spin current, and move the skyrmion, okay? And so here were the parameters for the current, for the SCT. And, and then their follow-up on that was start out with this value for the damping, alpha 0.1, run, see how that goes, and then experiment with different values of alpha and see how that affects things. And in particular, if alpha is equal to beta, then there should be no deflection of the skyrmion. It should move straight in the direction of the current. If alpha is bigger than beta, then it should drift upward in the way the problem was set up. If alpha is less than beta, it should drift downward. Now, the initial configuration that I requested had the skyrmion in the lower half of the strip, so that if alpha is bigger than the beta, it had room to drift upward. If you go for alpha smaller than beta, then it's going to drift downward and would run into the bottom of the strip. And so for that case, the homework was to flip the initial condition so that the skyrmion would start in the upper half and then move downward, okay? Now, the trick to doing that is to use a couple of vector field transformation objects, affine orient vector field and transform vector field. You need to use them both. Okay, sorry, to back up just a moment here. So here's what the spin torque module looks like. This is the A and V spin torque evolve. This is from IBM in Zurich originally. And you specify just the alpha, the U, the beta, And then the method, if you don't leave this, this is based on the Runge-Kutta evolver that comes in standard OOMMF. And so the author just added a spin torque term to it. And you inherit basically all this stuff that's in Runge-Kutta. And one of them is you can select which Runge-Kutta method you want to integrate with. And there's a number of them. The default is RKF54, which is a Runge-Kutta-Fehlberg 5-4 method. There's also the one with an extension S, which is supposed to be more stable. It's designed to be more stable. And I find that for the small values of alpha, it tends to go unstable, and that this helps keep it stable for alpha less than beta. And then, of course, the time driver. This is a time evolution system, so you need to use a time driver. And I'm going to be making a movie out of this. So rather than having some stopping criteria based on the torque, the stage stopping criteria is going to be a time. So here I'm going to stop every stage. A stage will be 50 picoseconds. And then I will print that out, save the magnetization state for making a movie. And then I have to list the number of stages I want. So this is going to be 4 nanoseconds, okay? The initial state, so the MS was fixed, whoever it was. The initial magnetization is going to be, I'll show you in the next slide, it's going to be one of the two positions depending upon the size of alpha relative to beta. Okay, so let me go here. So here's the setup. So when you come in, the initial field, so the default is M0, the initial position, is going to be just read from this file, whatever the start file is. And this is a file that you save from the energy minimization stage. So that's what you would get if you don't do anything extra. You have that initial position. But if alpha is less than beta, then I want to flip it. And so there are these two, affine orient vector field and transform. And so this one, the affine starts with the start field, the initial position. It will flip the thing. It will flip the position vectors, but it doesn't flip the vectors at each position. And so then that has to go through the second transform. I'll explain in a little bit more detail in a moment. It takes the output from this one, it goes into here and gives you the mirror start. So that's via mirror flipping. And then you set M0 to mirror start. So M0's either going to be the original file or it's going to be the transformed image from that file. And so you see back here, that's how the initial state gets picked, okay? So this is higher up in the file. You've got this check for alpha and beta. I do want to spend a moment talking about these two transforms on vector fields. You use these a lot for all sorts of sophisticated things, so I didn't want to mention them. The first one, affine orient vector field, it takes the input, so you've got a vector field f of r. R is the position, then f, the output's going to be a vector of that position. So what affine orient vector field does is applies a 3x3 matrix to the initial position, optionally adds an offset. So that basically shifts, rotates whatever the field, but it doesn't touch the vectors that come out, okay? So if you apply just this one, what would happen is your whole, your skyrmion would sort of be moved up, but it ends up, because there's a flip in here, it ends up turning the vectors inside out. So then you need to use the affine transform vector field, which applies a vector, applies a matrix, 3x3 matrix, and an offset after the transformation as well, okay? And you can look in the sample file for this, which is otprob1_2.mf, which has this all set up. And you can go through, then you can look at it in detail, okay? Okay, so when I run the simulations, I find that the deflection angle, this is the answer, right? The deflection angle is about 7 degrees upward if alpha is 0.1. It's 0 degrees if alpha is equal to 0.04, which is equal to beta. And it goes down by 3.5 degrees if alpha is 0.01. And at this point now, I'm going to show you what those states look like. Here. Okay. No, can I make this any bigger? No, I'm not sure. There we go. Okay, so this is the initial state with the skyrmion in the lower portion. And the damping here is 0.1. And this is I ran this thing and made this movie. And I'll show you how you make these movies later. But that's what happens. So it goes to the right. The speed is about 100 meters per second. And it's up, it's about 7 or 8 degrees, okay? On the other hand, if I set for the other value for the 0.01 damping, I had to do that. Hang on just a second. me bring this back here. So this is the initial state in this case. Okay, it starts in the upper left now, so you can see it's just flipped. Okay, and now of course when you run it, it goes down. Okay, pretty much same as before. Okay, let's go back to the slide deck. Okay, so some clarification that came up from in the questions since last week involving the destination and schedule commands, which you can put inside your OOMMF file. They set up default outputs. There was some question about how does that work? If you try to change it, does it set it back? And the answer is no. The destination and schedule commands, they're executed when the problem is loaded. If you reload the problem, they'll reset themselves. But they overlay onto any existing schedules. So if you have the solver already up, if you have Oxy already up and you have some schedule set and you load a new problem, any destination schedule commands in there will overlay the existing ones. Okay, so you end up with both of them. There is an option in Oxy to clear the schedule. So if you load a problem and you're not sure if there were some destination schedule commands, you don't want things writing to MM archive or running to your disk or whatnot, you can go and you can clear the entire schedule, get a clean slate, and then go in and interactively set the schedules that you want. Okay, so it's not sticky in that sense. Okay, right. Okay, so I want to talk a little bit about time varying fields. There's an example file, and it's actually session 3 and session 4 sample files called hping. And so this is an ellipsoid, and there's the long axis is along the x-axis, and we apply a field, a sync pulse actually, to a sync pulse along the y-axis, perpendicular long axis, and that'll cause the thing to process. And the sync field's nice. We'll talk about this more at the end. I'm going to do an example doing dispersion curves. A couple nice things about the sync is that in the Fourier transform space, it's flat until it disappears. So it's got a finite frequency response, so you don't have some of the problems with aliasing that you do if you use something else like a square pulse or something. You have to be concerned in the Fourier transform space, the FFT, that you're going to get aliasing from the higher frequencies. And also it's flat across the frequency range of interest, so you don't have to worry about scaling for the excitation. Okay, I'm going to use a Tickle proc for this. This is going inside a MIF file, so this is Tickle code. Tickle does not have a sync function in its EXPR command, but it's easy enough to make one. It's just sin t divided by t, and add a little bit of special handling here if t is really small, just to handle the 0 over 0 case, right? So that's just a function I built to implement sync, okay? The proc that I'm going to be using actually inside the script field file is sync pulse. It's going to take an input, it's going to be the time index, and it just computes this, it sets up the offset and the scaling that you want for the sync pulse, and then it sets hy equal to that. Most of the time evolvers, if you give it a time varying signal, they want to know what the derivative is also. It's used in time stepping. And so I need, in addition to sync, I also need the derivative of the sync, and that's computed here. And this function needs to return a 6 vector. The first 3 are the hx, hy, hz, and then the last 3 are the derivatives of those with respect to time. Okay, so I'm going to use the script uzmon for this. The u in uzmon is uniform. So this is a pulse which is varying in time, but it's spatially uniform. Okay, and like the other things that we've seen before, there's a multiplier you can put here, or you can put it into the function. Here's the script I'm running, script pulse from the previous slide. And then the parameters I'm going to send it, just the total time of the simulation. Okay, and that's basically it. Then we have the time driver. Okay, this is an ellipsoid. This is the initial condition that should actually be an equilibrium. Up to the discretization errors, this will be an equilibrium configuration for the ellipsoid, right? Because the DMAG field is uniform for ellipsoids on axis. Okay, all right, so that's, I don't want to spend more time on that. The sample file is in, hping is in the sample file list, so you can look at that more carefully. I do want to talk about a more complicated transform. This is for Zeeman fields. So these are applied fields. So in this example, I use the uniform applied field. Sometimes, of course, you want a field which is varying spatially as well as in time. And in particular, you may want to focus and have a small portion of the simulation see the field and not the rest of it. And you can do that with the transform Zeeman class, provided that you can break your fields. Normally, offhand, right, your applied field is going to be a function of time, x, y, and z, okay? If you can break it up into a function of position, this is an arbitrary function of position using any of the vector field objects in OOMMF, and multiplied by a time varying matrix, actually. So this can be a diagonal matrix, in which case you're just multiplying by a constant. That's the most common case. So the idea is that you have your vector field here, which is, you can think of it sort of a selection field, where it's one, say I had a disk that I want to have the field and not see it anywhere else. So the function would be 1 inside the disk and 0 outside. And then you multiply it by your time profile, which starts out at 0, for example, and then maybe grows up and comes back down, or it can maybe oscillate like a sync pulse or whatever it is. This will then basically restrict that pulse to just that region where this thing is non-zero, okay? And of course, you can shape this also. This is big in the middle and small on the edges. Then when you multiply it together, you'll have a signal which starts out at 0, at time equals 0, and then gradually grows and does whatever you're specifying here in your time profile, and then come back down. And I'll show some more examples of this when I do the dispersion example. Okay, it doesn't have to be a constant for transform Zeeman. It can be a matrix, and so this matrix actually can do rotations and stuff like that as well. Okay, so it's actually pretty flexible. As with the UZeemon class, the script that comes back, this is also a script class. It has to return a 6 vector, which is both the field, hx, hoa, hz, but also its derivatives, okay? Now, just pro tip. Every time you're using any of these time varying applied fields and you have to compute the time derivative, when you run the simulation, keep an eye on the time step. It's very easy. I know it's just differential calculus, but believe me, it happens that when you go to write the code to compute the derivative, that's this thing here, you screw up, right? You miss a factor or something. And if you get that wrong, if you get the dHdt wrong, then the time stepper is going to basically say, oh, something's wrong here. It's going to collapse the step size. So if you keep an eye on the step size and it gets down to like 10 to the minus 20 seconds, your system is not going to evolve. It's just basically going to be stuck. And that's the most common cause when that happens, is that you've made an error when you computed dHdt. Okay, so watch out for that. Okay, just like you can have a time varying applied field, you can also have a time varying current for things like the spin transfer evolve. And this is the same sort of thing. I set up a sync here. You have a sync pulse just like before. This one does not need a time derivative, okay? So that's a little bit simpler. And then inside your transfer evolve, you specify u. In the examples that we have, for example, spin ping, this is just a constant. But that u actually can be any vector field. I'm sorry, be any scalar field. It's the current density, and it's allowed to vary in space. And so if you, and in this spin ping example, I have a u profile. This is the time variation. Okay, so that's here. So this is what your current profile looks like in time. And the current that you actually get at the current density you get at any point is given by this product. Okay. Okay, so that's pretty flexible again. It's not quite as flexible as the transform Zeeman, where this thing can be a matrix. It's just a scalar multiple. Okay, another thing, another sort of advanced concept or more advanced simulation is to model an infinite strip. Okay, so I have here, for example, and this is actually taken from a paper I did with Bob McMichael a long time ago. We had a head-to-head domain wall, and so we're interested in what's happening here. You get away from the domain wall, and the magnetization is due to the DMAG, the shape anisotropy. It wants to lie parallel to the strip. Okay, but if I just cut the strip off, because I only have room in my computer for a finite number of spins. If I just cut that off, I'm going to get a charge plate here. It's going to be all these minus charges on this side, all these plus charges on this side. That's going to give me a stray field, and that's going to affect things. Okay, and the stray field actually extends quite a ways. So I'd like to correct for that. So one way to do this, well, basically what you want to do is, this is going to have, from the simulation, I'm going to have minus charges here from these vectors on the edge. So I want to put plus charges here. So before you do this simulation, you do a preparatory simulation where you take a strip which you make as long as you can manage, basically computationally. Set the M uniform in that strip, load it up into Oxy, and then without taking any steps at all, just output the DMAG field. And that will give you the DMAG field that comes from a charge plate here, positive charge plate here, and a negative charge plate way out at a really large place. If that strip is long enough, then the field that you see from the minus bits is going to be very weak and not going to have very much effect. So that stray field that you get from these from here, from the whole thing, is basically the same as a charge plate, as a field from a charge plate. And so then you can basically attach that to the end. And you can see this file for an example of how to do that. To get the left side, it's the same thing. You can just rotate it. You can use these script orient or affine transform transformations for vector fields I showed you before that you can use on this as well. Okay. And then the only other trick is you also, these spins here on the end, you want them to stay aligned, and so you put a small border region on the ends here, and you fix the spins as I showed last week. And again, look in this file for examples. Okay. And this technique is also discussed in more detail in this paper if you want to look it up. Okay, this is an important one here. User-specified data table outputs. Okay, so this frequently comes up. If you look at the scalar output that you get when you run a simulation, you get like mx. That's the average value of mx over the entire simulation. It's often the case where you want to know what the average magnetization is in some subset, some sub-region of some sub-volume of the entire simulation. So for example, if you've got a multi-layer film, and the bottom layer is pinned and the top layer is flipping, you want to know what the magnetization of the top layer is doing, not the whole thing. Okay, and so to do that, there is something called user outputs. Okay, that's a specify option that's available in most, if not all, of the OXT objects, at least the ones that produce output fields. The description for this, the details on this, are in the MIF 2.1 section of the user's guide. You may remember when I talked about OXS, about Oxy, that the data in the user guide that you're interested in is in two places. For the classes themselves, for the XT objects, the drivers, the energies, the evolvers, that's all going to be in a section on the OXS, OXS extensions objects. That's where that information is. There's also, though, a lot of information that you need for writing a MIF file, which is in a different section of the documentation on the MIF files, MIF 2.1 files. And that's where the user outputs are defined and documented. And that's because it's common to all of the EXT objects. What it does is you specify, and I'll show you what it looks like in the next slide. You take your source field, for example, the total magnetization, which varies point-wise. So this is at a particular step in the simulation. You have the magnetization, it's varying point-wise. You have a select field. This is another field. It's just another vector field in OOMMF using any of the vector field classes. And what happens when you on this output is it takes the dot product of these two vectors, sums it across the entire simulation, and then weights it by the sum of the select field. So, for example, frequently this would be like the magnetization. This would be an indicator, a characteristic function for something. Like if I have a 3-layer film, maybe this is 1 on the top layer and it's 0 everywhere else. Okay. Well, actually, this is a vector field. So this is maybe 1 along the x direction, 0 along y, 0 along z. So this would be 1, 0, 0. If you're in the top film, the top layer, and 0 everywhere else. And so then I take the magnetization, I dot that against this. If this is 1, 0, 0, I get the mx component. If I'm in the top layer, 0 everywhere else. Okay. So I add up, sum up all the mx's in that top layer, and then this just adjusts for the weighting, so you get a unit score in the end. And then you have the mx component for the top layer. Okay. If you want the my component, then you have to have another user output where this field will be then 0, 1, 0, okay? It's not as common, but this thing it doesn't have to be a constant step function. You can have this vary however you want. If you want to have different weightings in different portions, okay? So this is what it looks like. So for example, inside the OXS min driver specify block, you put all the stuff you usually put, and then you specify user output. The first field in here is name. That's the name, which is going to, this is going to be a scalar output, right, for each step. It's going to show up in the data table output, okay? This name is the name that gets attached to it in the data table output. I'll do an example in a moment, okay? This is a source field. This is the thing which is varying from the computation. Here it's going to be magnetization, because magnetization is an output of the min driver. And then I have my select field. I didn't show it here. I called it, I have somewhere else above, I have a vector field called top X. It selects the top layer of the film. I'll show you in a moment what the film looks like, what the simulation looks like. It's the top layer of the simulation. And X means it selects the X component. So it's 1, 0, 0 in the top layer and 0 everywhere else. Here's a scaling factor. For this particular example, I wanted to normalize. For this particular example, the MS value was 1400 kiloamps per meter. And so this just makes it a unit vector. And likewise, I have then a second output, which is the bottom layer, the X component of the bottom layer. Okay. So let me go ahead and see if I can bring that up. Bring this down here. Okay, so there's Oxy. This graph widget. I already had these set up. I already have the problem loaded. It's called user outputs.mif. It's in the samples file. Let me show you what it looks like here. Magnetization. What's going on here? All right, there we go. A little bit sluggish. Okay, so this is a 3-layer film. There's the bottom layer, magnetization pointing to the right. Middle layer is a vacuum and non-magnetic, and the top layer is pointing up to the whatever angle that is, 45 degrees. If I flip this on the end, you can see the layers. Let's just there we go. Okay. So you can see there are 3 layers. This one's angled, so it's a little bit smaller. But I want to see the whole thing, so I'm going to look back from the top. I'm going to show you a little trick here. I want to see both the top and bottom layers at the same time. So I'm going to go into the configuration option for MMDisp. I'm going to leave the pixel display turned off, but I'm going to color the vectors instead of by Z. I'm going to color them by slice. So this is going to be the vertical component on the display, which in this case is Z. So the bottom layer will be one color, the top layer will be a different color. And I want to see them both all at the same time. This particular simulation, the thickness of the cells is 3 nanometers. That's typically what MMDisc uses for the arrow span. So this is how many layers am I seeing in depth. It usually shows you 1 at a time. If I kick this up to 9, and I recenter this thing, you can see 2 vectors here. So the red, you see here Z, that's red is minus Z, minus values. So the red layer here is the lower level, the lower layer, and the blue is the top layer. If you look closely, you can even see the arrows drawn on top of it, okay? So now I can see both layers at the same time, so that's kind of convenient. In this particular example, there is a bias field on the lower layer, so it's going to tend to stay put. I'm going to be applying a field. The initial field I'm going to apply is a strong field to the right, which will saturate both layers. And then I'm going to reduce the field and run it through a half hysteresis loop. The top layer will shift first because it's free to spin, to rotate. And the bottom layer, it's pinned, it won't go as early. And we'll see what happens there. And I'm going to send the output here. Now you'll notice, I already have this set up. So the x-axis is going to be the applied field, Bx. Okay, the y-axis is going to show 3 outputs. So MX, min driver MX, that's the average MX that you get anytime you run an OOM simulation. Here are my two user outputs that I just invented, right, that I just put in. There's top and bottom, okay? And it's MX top and MY bottom because I chose the X component, okay? So those are all being shown here, and there'll be different colors. Let me go ahead and relax the first state here. Okay, so when I relax the first state, you can see here that you can barely see that there's what the lower level is, the lower layer, okay? So the spins are basically aligned about the top and the bottom layer. Okay, and now I'm going to relax a little bit. Actually, let me go in here, make this a little bit easier to see. I'm going to go into the configuration for the graph widget, and I'm going to change the curve width, make that 2, just a little bit thicker. There we go. Okay, and so here we can see the middle here, that's the MX, that's the average. This is the bottom layer on top. The top layer is on the bottom. It's already starting to shift. This is 1 would be fully saturated, -1 would be the opposite direction. So let's just run this for a little bit here. And you can see as the system evolves that the layers are starting to decant relative to each other. Okay, let's just wait here a moment. Okay, and let's keep going. Okay, we're still nearly saturated. This is 0.95. So we're still nearly saturated, but not quite. The top layer is starting to flip, as you can see in the diagram to the left. Okay, so now I'm just past the remnants. There's applied field is now to the left. The top layer, which is blue, has flipped, as you can see here. You can also see here in this the violet color that it's flipped all the way. It's almost -1 here. Okay, the top layer, on the other hand, actually rebounded a little bit and went a little bit more to the right. Okay, and the average is close to 0 here. Okay, well, I'm going to show you another trick on an OOM graph. If you place the cursor on the left axis and you click, and see if I can get it here. No, there we go. There's a little movable axis. Okay, and the coordinates here by the arrow, that's the coordinates of the arrow point. So there's 46. So I can move this down to, for example, close to 0, and that's where the 0 axis is. Okay, and likewise, there's another one down here, which I got first try. Okay, but you can move, and so you can put this anywhere, and it helps you see how flat things are. You can read off what the values are. Okay. Also, though, if you just click on a point on the graph, it will tell you what the coordinates are on that point also. If you use the left click, it will tell you the Y value from the left-hand axis. If you do a right click, if you have the second axis set up, if you have Y2, a right click will tell you what the coordinates are on the right axis. So let me just run this on out now. And you can see that it takes a little while. This top layer here, I'm sorry, the bottom layer will eventually flip. Okay, it's thinking, that means it's flipping. There it goes. Okay, so this was a energy minimization simulation. Okay. All right. Any questions? Okay, so let me answer a few questions here. How do we determine which RK method to choose in general? So if you don't specify the Runge-Kutta method, you get the default, which is, and there, if you look at the documentation, it tells you what paper these came from. It's a good compromise between accuracy and stability. Most of the time it works well. If you're, just use that one unless it goes unstable. If the simulation goes unstable, which you can tell because it just goes nuts, try using the RKF54S because it's a little bit more stable. If you're running at the really low damping, damping of course helps dampen out numerical errors as well as other sources of perturbation in the system. If you have really low damping, then that can sort of build up. And I think Don and I wrote a paper on this. It turns out if you use, there's another method in there, it's RK4, so you store your standard 4th order Runge-Kutta. Because of some details on the way that the spins are normalized to keep them on the unit sphere, It turns out that the RK4 sort of artificially adds in a little bit extra damping. And so if you're running in a low damping regime and it goes unstable, if you use RK4, that tends to be more stable. There's also a couple RK2 methods. I don't know any particular reason to use them, but for comparison to other simulations you find in the literature that might be useful. Is the norm 1 really needed in the file vector field? It is not needed to set up initial magnetization. Okay, the initial magnetization will do an auto scaling. So if you're using a file vector field to set the initial magnetization, which is how you usually use it, then no, you do not need to specify norm 1. Okay, if you're loading it to something else, then you may, if you want to be normalized, you need to do that. If you don't want it to be normalized, you want the raw field values coming in, then you don't use it. Okay. Okay, so here's the next question. How do you know the degree of change in the skyrmion path trajectory? So I just pulled it up in MMDisp, and so I had it stop at one stage, and I clicked here. I did a Control-Shift-Click, and in the middle of the skyrmion, and that gives me the location. And then I let the thing run some more. I recorded that, and then I let it run some more, and then the skyrmion was over here. I did a Control-Shift left click again, and I got a new location, and then I just took that difference, computed the angle, and the distance. Okay, next question. Can FR be equal to magnetization on the previous step? If not, is there a way to apply a magnetic field which depends on the magnetization and also varies with time? I'm laughing a little bit because this question actually came up in my inbox about a month ago. The standard answer on the stock OOMMF is no. F of R is set at the beginning. It's a fixed value. Well, yeah. So FR, you can change it at stages. You can change it at stages, but it can't be tied to the magnetization directly. However, I do have, I put this together for a user, a preliminary attempt at allowing these sorts of things. So if you really need to do that, shoot me an email. I will send you the code that I have, and you can be a pre-alpha tester even, okay? Okay, I'm going to move on now. Let's see, what's next here? Let me just bring these on. Bring these out of the way, go back to my slide deck. Which is this one. Okay, so any questions on user outputs? I guess not. All right. So they're very, very useful. A little bit tricky to use the first time, but they're very powerful. Okay, so now I'm going to talk about command line tools that are in OOMMF. The first little trick. So when you want to run the command line tools, the canonical way to do it is you run tickle, you say tickle sh, the path to oomph.tickle, and then whatever the parameters are that the file that the command line tool is the first thing, and then parameters to that. Frequently though, you've got files that you want to operate on which are somewhere else in your operating on your disk drive. They're not close to oomph. And typing in the full path to oomph is a bit of a pain. So on Windows, I have in my path, I have a file called oomph.bat. It just has this one line in it. And that allows me then to run command line tools by just saying oomph command line tool parameters, okay? On Unix, you can do the same sort of a thing. In that case, I have a bash, I use bash, everyone uses bash now, right? Yeah, it's the same thing, tickle sh, then the full path to the oomph, and then $* in quotes is what you want to use on bash so that all the parameters get passed through. Well, on Windows, the batch file, it's %*, that passes all the parameters that were on the command line onto the thing. Also, when I'm running these demos, there are a number of command line utilities which are default on Unix systems. They're not on Windows, but you can install them on Windows. For example, there's a project called GNU Win32 where you can go in and download all sorts of utilities for Windows that come from Unix. In particular, this is a set of 5, which I use a lot. I'm going to be using grep and less. Less is like more, but it's more because less is more. Sed is a streaming editor. I may do one example using sed, but less I'm going to be using a lot here, just to view files, just mostly to show you. grep allows you to go in and it also allows you to feed a file in. It's a filter. You read a file in on standard in, and then it writes out the standard out, and it has selects lines or deselects lines. Oh, I guess one other point. If you're on Unix and you set up a wrapper like this, you have to remember to make the wrapper executable. So use change mod. Okay, so the first tool I'm going to talk about is ODT calls. Okay, this is a utility that works with the scalar data output, the data table files, OOMMF data table. It allows you to, if you look at the output, when we, for example, in the previous, when I was looking at the tri-layer film or looking at all the different outputs, that list of outputs that comes down from mmgraph, those all those outputs show up in the data table file that you save in MM archive. It's a long list, and usually you don't want all of them. So this tool allows you to pull out particular columns, so you don't have all the columns. It also allows you to convert to other formats, which are easier to import into spreadsheets, okay? It acts as a filter like grep, so you have to remember to put things in on standard input, which you use with the less than sign. And it writes out the standard output by default. If you want to go to a file, then you do a greater than sign to send it to the output. So let's do a couple of examples here. Bring up my command prompt. Okay, so let me get my bearings here. Okay, so let's take a look first at a, okay, let's bring this up. Okay, so now let's look at a sample ODT output file. Prob1, so this is the homework problem. This is an output from the homework problem. This one, let's see. So let me pull this up. So this is what the ODT files look like. If you send output, data table output to MM archive, this is what's going right in the disk. Okay, it's got the header line ODT10, so you know what it is. The start of a table, if you look at the end of the file, which is here, there's this table end. You can have multiple tables inside one file. They're separated by the table start and table end. Every table has a title and then a list of the columns, okay? The format here is designed for easy reading into Tickle. So this is the space protection mechanism that's in Tickle. So this is one column here, even though there's space in here. So the first column is total energy, then energy count, and so on. They're not in any particular, well, yeah, I'm not sure where the order comes from here. To tell you the truth, I'd have to check. Then the second one, this is a long line here. It's just wrapped because the screen, right? The second line is the units. And so those are the units that are associated with this. So the total energy is measured in, I don't know where that is. Here it's going to be joules someplace. There it is. There's the first column, joules. And then after that, then you just have line after line after line of data, okay? And it goes all the way through. And the number of columns is fixed up here, okay? So even that's just, you know, it's hard to read that even. So the first thing, so there's my little shortcut to OOMMF. ODT calls is a command I'm going to use. Okay, this is a filter, so I need to put in the less than sign here. And -S for a summary. Okay, and it tells me that there were 19 columns in that file. Here's what they are, okay, in the order. And this just numbers them. These are the units. It tells you the number of columns. Yeah, there are 20 columns. They go from 0 to 19. It also tells you the number of rows in the table. If there are multiple data tables in the file, then they'll be listed here. If you, all the command line tools, which are all the OOMMF tools, if you run from the command line, you do a -H, it'll give you a little help prompt. Some of these are longer than others. ODT calls, for example, capital S or lowercase s gives you a summary. The -T output type, that allows you to convert to a different format. You can also do some formatting so the columns are easier to read. You specify the width of each column in spaces, and the format is a printf style. If you have multiple tables, table select allows you to select which of the tables you want to send to the output file. And mainly you specify here the column that you want on the output. You can either do this by the name or the number. If you use by name, you have to be careful you give it a unique name, so it's usually easier just to do columns. So if I go here and I'm going to specify some columns, what should I decide to do here? Okay, 14, 19, and 2. So 14 is going to be the stage number. 19 is the simulation time. It's going to be in seconds. And number 2 is the max DMDT, okay? And I'm just going to pipe that into less so we can look at it on the screen. And here it is. So now I have just 3 columns, okay? Okay, they're kind of big, so they overlap each other. But if you were bringing this into a spreadsheet or something, this is basically okay. You don't need to worry about that. Okay, but if you want to make it look prettier, I can specify a column width of, let's say 20. And I'm going to specify a format. It's just -F %pound 10.6G. You need to play with that. Okay, and let's see what that looks like. Okay, so now it's all prettified, right? So you can make this as long as you want with your format specifier and the spacing, right? And so here you see the first one is a stage, no units on the stage number, simulation times in seconds, the MDT is in degrees per nanosecond, okay? Now, there are many programs which will take that. Let me bring that back up for a minute here. There are many programs that will just take this as it is and read it. For example, I use GNU plotting software. It ignores any line that starts with a pound sign. Lots of programs do that. So you may be okay just importing that as it is, but if whatever you're bringing in is a little bit finicky, then you may want to convert it to a different type. So there's a T specifier. There are different outputs, different type outputs. You can strip the, one of them is bare, which strips the headers, but one of them is also CSV, okay, comma separated value format. Okay, and in this case, this is the standard interchange format for spreadsheets. Okay, so here's the header. The header is preserved. Everything's separated by commas. Okay, so you got commas. Okay, let's see. One of the questions I got on the, I think it was in NanoHub, asked if you notice here that the column headers, they have the full name in here. Okay, one of the questions that came in was, can we put just the end part? Can we get that somehow? And there's no direct support in OOMMF for that. However, if you've got command line tools and you're familiar with them, you can strip them out before they go to the output. So let's see if I can get the magic string in here. So I'm going to use sed, which is streaming editor. S is for substitute. Okay, I want to strip off anything. Let's see if I can type this properly. If it doesn't work, then I typed it in wrong. Okay, where are we at here? First, I'm at the end of the line. So anything that begins with an OXS or an ANV and then continues without a space until I get to a colon, I'm going to replace that with the empty string and then do that as G means globally, so on the entire line. So if you do that, then it's stripped out the first part and you get the short form here, okay? Okay, you notice there's no header at the bottom either, right? So, okay, that's all I'm going to say about ODT calls. So again, for bringing that, it's useful for lots of different things if you're working with the data table format. Data table output. Okay, the next thing I want to talk about, let me just go back to my slide deck. Okay, and those are just here on this slide deck. I just gave you the commands. Miss anything? No. Oh, in addition to ODT calls, which can pull out particular columns from your data table, there's another application called ODT Calc, which takes existing data and produces new columns. So you can use this to add columns. So for example, if you're running a hysteresis loop and you have a field which is applied off axis and you want to know what the magnetization is projected to that axis, you can use ODT Calc to do that. It uses Tickle EXPR commands to combine columns as you wish. Okay. I also mentioned here just while it's on my mind. If you type, if you take oomph or tickle sh oomph.tickle and you try to run the help command, it will list all of the different things, all the different commands which are available in oomph. So you see ODT calls is here, ODT cat. These are also all documented in the user guide. The command line tools are in their own section, command line tools section. All right. The next one I'm going to talk about is AVT to ODT. So this one, takes an OVF file, so a field file, typically magnetization, but it can also be any of the field files, and we'll convert that to a data table. Okay, so in particular, it goes into that file and can do averaging along different affine subspaces. So, for example, this is the homework problem. Okay, if I want to know where the skyrmion is at in a particular stage, so when I ran the simulation, I printed out the magnetization at each stage. Okay, and I put it in a file like this. And then if I run OVF to ODT, and I'll go through this in detail in a moment, but if I say average on a plane which is perpendicular to the x-axis, so you may remember, right, we've got the skyrmions moving towards the x-axis. If I take a plane which is perpendicular to that, so parallel to the YZ, and I average all the magnetization in that plane, and then I step that plane across the entire simulation, then I'll have the average magnetization. How strange I did MY instead of MZ. This may be mislabeled. This is probably supposed to be MZ here. My graph. But in any event, it pulls out the MX, MY, and MZ components along those planes, and this gives you a line graph basically. And so I plotted the output in this little figure here. So this is the initial state. You can see this is, like I said, this is actually the Z component. There's one place here where the center of the skyrmion is, and it's at this offset. Okay. Then I let the simulation run for a while, and I get to 2 nanoseconds, which happens to be stage 39, and I run this. If I run this again on that command, on that output file, then I get this green line here in the middle. That's where so you can see the skyrmion has moved to there. And then this is at the end. This is at 4 nanoseconds. Okay, so let's step through that. Oops. Okay, so I'm going to use AVF to ODT. Actually, let me pull up the help listing for that first off. Okay. And I'll just do it this way. Okay. So it's not it can take a file name, or if you don't specify a file name for the input, it reads from standard input. The first option here is the averaging type. Okay, so the manifold that you want to average over. So in the example I just showed you, I was averaging over planes. You can average over a line. You can average. Don't do average at all, that's a point. You can average over the whole space. I'll show you that in a minute. There's also an option where you can average over a spherical region. If you're using the plane or line, you have to specify an axis. So if you specify a plane, then you specify the axis which is perpendicular to plane to select it. If you're using a line, you have to specify direction parallel to the line. These are only planes and lines which are parallel or perpendicular to the coordinate axes, okay? So let me run a little example here to clarify. Actually, let's look at an example file. OT prob 1, 2, at stage 39, for example. Okay, so this is what the OVF files look like. Okay, they have a header. This is an OVF version 2 file. There is a header which tells you all sorts of stuff. It tells you the size of the steps, the cell size. It tells you how many nodes you have in each direction. It tells you the base point. Tells you the minimum and maximum values. These are going to be in meters. So this file runs from 0 to 500 nanometers by 200 nanometers, and it's 6 angstroms tall. And then the number of values which are in each line of the field. Okay. And then this particular file, after the header, you have an end header message, and then you have the a label here that the data is beginning. And there's 3 types of data blocks that can be binary, 4-byte binary, 8-byte binary, or text. Okay. The binary formats are nice, they're a little bit more compact than the text, but also they read and are written much faster than if you use the text format. It's a big file, it has to be converted in and out. So the binary is kind of nice for that. But if you're going to bring it into any other program, you want to convert it to text. So that's where that's used. Okay. And then at the bottom, again, there's another 2 lines here, ending the data section and then ending the segment. Again, all the header lines start with a pound sign, okay? So if for some reason you need to get rid of all the header lines, it's relatively easy. You can send it through grep, for example, and deselect on the pound character. Okay, so that's what the input's looking like, okay? If I wrote it out in text format, you'd have 3 columns, which are the MX, MY, and MZ, okay, all the way through. So now, let's bring this into AVF to ODT. The VF is vector field. And let's do that example I just showed you on the slide. So my average plane, we want to use the x-axis, and I'm going to give the file, and you can give multiple files here, okay? And so, and you can wildcard. So yes, you can convert a whole bunch of files at once to create a long data table. Well, I'll do this in one of the later examples I'm giving in, I think, the dispersion curve one. But let's just send that right now to send it out and take a look at it. Oops. Let's try that again. Let's just select the output file. One file, dash. So commonly in these command line tools, if you specify a file name as dash, it goes to standard output. Or if it's for input, it reads it as standard input. Okay, so here's what the output's going to look like. So there's one, so these are averaging over planes, and the planes are moving across the simulation. So X here is the coordinate of the plane as it moves from 1 nanometer, 3 nanometers, 5 nanometers. Remember the cell size is 2 nanometers in the X direction, so that's why you get this stepping. For each plane then, it gives you the MX, MY, and MZ values, okay? That's if I do an averaging on plane. You can see here, there's the cell size, the number of cells in the active volume, talk about that in a minute. The averages across the x-axis. So in each plane that I'm averaging, that's the number of points I could average to give you these values, okay? If instead of averaging on a plane, I decide to average along an axis, and I'm going to average, say, along the y-axis. Now, this particular example, this is a standard, this is the homework problem. It's only 1 layer thick. So if I average along the y-axis, or I average along a plane perpendicular to the x-axis, it's the same thing in this case, because there's only one. However, in general, again, what's wrong here? I can't type. This is supposed to be a line here. Sorry, average along the lines. Now, in this case, these values should be the same as before. But now, instead of having a x-coordinate, I get 2 coordinates, which are the orthogonal coordinates of the y-axis. In this particular example, z is always going to be 3. If you go all the way down to the end, you see it doesn't change. But more generally, if you have, you know, a 3D object, it's going to be more points, right? So this is going to be all the 2D points that have some y-axis. Okay. If you say, instead of a line, you put point. Okay. Then you get all 3 coordinates. This is not averaged at all. So you see there's nothing averaged there. Points in specific volume. So this is just X, Y, Z, MX, and Y, and Z. So you can use this to export an OVF file into some other program which wants the raw coordinates. Okay, and I think we do this later in this talk. And likewise, if I go space, so point and the space do not require an axis because it's already determined. Okay, in that case, I don't get any X, Y, or Z coordinates because it's the full space. And it tells you the number of cells is 25,000 in this case. And that's the average. So this is going to be the same as the MX, MY, and MZ values that you get from the data table output. Okay, now let me look a little more closely here at the help listing. Okay, so that's the average, the axis. Okay, by default, you get out default position. So that's going to be X or XY or XYZ. Those are the coordinates that come out. You can turn those, by default, you get those. If you don't want them for some reason, you just want the raw data, you can turn that off, okay? Likewise, by default, you get the MX and Y and MZ values. If you don't want those, you can turn that off. You can specify some extra outputs. You can get minimum and maximum values and excuse me, L1 and L2 values also. Read the documentation if you're interested in that. If you're processing a lot of files and you're outputting them into a single file, you may want to adjust the sorting method. So you keep an eye on that. Header style. What I showed you was the full header. If you have multiple files, if you select collapse, then they get put together with only the one header. Sometimes if you're importing to another program, you don't want any headers at all, so you can specify none, and then you just get the data without any headers. If you have multiple files, you can add an additional column, which is an index for the file. So you have a column that tells you which file that particular data came from. There is also, you can specify different ways to specify which files come in if you're wildcarding the input. You can specify what the output format is. Again, it's a printf string. By default, if you have a bunch of files, each file is printed out with ODT instead of OMF or OVF at the end. So you can process a whole bunch of files at one time. Here's one I do want to mention, the region. So you can specify, if you don't want to work over the full simulation, you can specify a rectangular subregion, and it will work only on that subregion. And so when I go to do the dispersion study later on, I want to know what the file values are just along a strip in the middle of the full simulation. And so I'll use this program with the region selection to select just that middle, so you can get data for just that portion. Okay. And then you can also, like in ODT calc, you can use an expr command with some variables to produce secondary data from that and have that come out in a column, okay? In particular, in one of the examples later, I want to have just one component of the magnetization. So what I do there is I turn off the default output, default position, default values. So by default, nothing comes out at all. And then I'll use this val func and I'll point out $VX, for example, to get just the MX component. Okay. Question, is it possible to join only one column of each ODD file into a single file? Yes. For example, column one of one ODT and column one of ODT into a single file. I'm not quite sure what the question is. If you want to put them together parallel to each other, you have to use some tool, some Unix tool like paste or something to put them together. I don't have support for that directly. If you want to append them one after the other, then yes, it will do that by default. And actually, that's what I'm going to do in one of the other examples. Okay, but yeah, we don't have any facilities in place to paste them side by side right now. Okay. So what's next? Let me check my slide deck here. Oops. Well, actually, maybe we should take a short break here. This may be a good place for a break. So the next thing we're going to talk about is let's see, what's the next thing? This is a surprise. Let's see. Okay, creating images. Okay, so you have some vector field that you save, probably your magnetization, but maybe some other field, and you want to create a picture, right? Either put in a publication, or maybe you want to make a movie or a presentation, send it to an abstract, whatever. So you take your file, and usually the first step is you load it into OOMMF. Okay, you configure it to be approximately what you want the picture to be. You save the configuration. I'll step through all this in a moment here. Then you go in, you edit the configuration file, you tweak it a little bit. There's some things which you commonly tweak. These are the common ones here. And then you run a command line tool, AVF, again, vector field, to PPM, this is a bitmap format, or to PostScript format. And that creates a bitmap or a PostScript format. The PostScript format, I should do some work to make a PDF output. PostScript is pretty easy to convert to PDF. And the nice thing about PostScript or PDF is that the arrows are represented as vectors, scalar SVG, scalar vector format, graph, whatever it is. So they scales. So if you're doing a publication, you have arrows there that's in the drawing. This allows you to scale without the whole thing going jaggy. So I like to use this when I can for publications, but for making movies, you need to have a bitmap format, or I find that in abstracts, typically they don't take PDF files, they want JPEG or something, and so you want a bitmap format. By this thing, AVF to PPM, it writes to PPM format, which is an old Unix format, uncompressed, full color. Alternately, there's a switch you can put on to get the Windows BM24 format. It's an old bitmap, uncompressed 24-bit bitmap format from Microsoft. You can use either one of those, and you can bring them into another program to convert them. But also, there is a program in OOMMF called ANY to PPM, which will convert either of those formats to, for example, to PNG. And I'll probably actually change AVF to PPM to do PNG output by default even in the future. It's easy if you have TICL 8.6. And this will convert your file into a bitmap format. So let's step through that. Okay. So let me go back to my command line. And I'm going to launch into OOMMF, which you can launch OOMMF from the command line. And I'm going to give it the file that I want to load. Which one am I doing here? Oh, great. Okay, here it is. OT. Yeah, okay, so I'm going to go back to the homework problem again, since we're all familiar with that one. Okay, and stage 39 OOMMF, all right? So that's 2 nanoseconds in. So I'm going to open that into OOMMF. Okay, so there it is. Okay, so I'll pull up the configuration here, and I want to have, I want to turn the pixels on, and my color the z-axis, say with respect to that. So I have this sort of thing. You can change the subsampling here. That's usually, you get this thing, if you know about the size that you want. Okay. Well, maybe, here we go. All right. Machine's a little sluggish today. Maybe I should pour some coffee in it. Okay. So you size it up to be about what you want. In particular, look at the subsampling on the vectors. How many you want. You can turn that off and adjust it and say, oh, I want more vectors. You see how that looks. Oh, maybe that's too big. Maybe that's too small. 8, say, whatever. Okay, so you play around with that until it looks basically what you want. And then you go over to File, and you go to the Write Config option, okay? And then these files, you want to give them an extension .config, and it will write it out, okay? So I did this already for this particular problem, and I got this configuration file, okay? And so you select the name of the file, whatever, foo.config, and okay, and you've written it out, okay? And then we're done with OOMMF. right? So let's take a look then at foo.config, for example. So this is what the configuration files for MMDisp and the various AVF to PPM or AVF to PS, this is what they read, okay? So this is actually, again, this is all ticklish. And then this is a tickle array here. So this reads easily into tickle. That's why we use this format. There's a section here that concerns the array, the arrows. So if auto sample is 0, then there's no auto sampling. Instead, the sampling is determined by this value here. You can select the color map, which presumably you already did in MMDisp. You can adjust the number of colors that you want. There's a couple options here which are not available in MMDisp. You can, well, you can offset. You can offset in the color map. Color reverse is actually available inside MMDisp. You can change the size of the arrows, make them bigger or smaller. Status, 0 or 1. If it's 0, then you don't get any arrows. If it's 1, you do. I'm going to go here. This is what you get from MMDisp. If you look in the documentation, there are some additional settings which are put in place for these other conversion programs. And what do I have here? What I called it? Okay, so let's look at what I did earlier. Okay, so in particular, there's an anti-alias option for arrows. So that smooths the edges a little bit, which is generally a good thing. It does increase the number of colors in the output file. If you're trying to use something like GIF, which has a limited palette, then this is bad. But if you're working full color, that's usually not an issue. The quantity that, all the stuff you usually see. The data scale setting, I didn't mess with that, but you can adjust this also. This is essentially contrast. Okay, here's a couple key ones. Typically, when you're creating files, your images, you know what size you want. So you set the size here. And if you want to show the whole image, turn the zoom off by setting it to 0. And then the program will automatically fill the space to use all this thing with the full image. The only reason why you'd want to use zoom that I can think of would be if you want to magnify and see a small section of the full image. There's a crop setting. So you specify these dimensions. If crop is enabled, meaning 1, then it will fit to these dimensions, and then any leftover white space will be cropped off. That's usually sort of what you want, unless you are importing it and you're going to be making a movie out of it. A lot of codecs have limitations, have restrictions on the size of the individual frames. Typically, they want them to be an even number, for example, or maybe even mod 4, 0 mod 4. And so in that case, the cropping can mess you up. So usually what I do in that case is I turn the cropping on, I see what size I get, then I bump these up a little bit larger so it's close cropped, but has the dimensions that I want, and I turn the cropping off. If you're displaying the full simulation, you're going to want the thing centered. So this is the relative X, relative Y, relative Z. So between 0 and 1. If you're zooming in or you want to focus on some point off-centered, then you need to put in the proper coordinates there. These, you can get these from MMDisp. If you center it however you want in MMDisp, that will show up here. There's also a rotation option, but this is just 90-degree increments. So it's nothing finer than that. Okay, so then there's also, similarly, you have settings for the pixel numbers also. Pixel status 1 or 0. The view axis, again, these would be set by MMDisp. And the span, I showed you earlier how you can change the arrow span if you want to see more than one arrow at a time, and that's in the depth. And there are some additional ones. These are used by the AVS to PS program only. Okay, I'll get back to that question in a moment. Let's see. So that's what the config file looks like. And then once we're happy with that, then we will use AVF to PPM to make a bitmap. And let me just look at the help listing for that. Okay, so the format, the default is this PPM format, but I'll show you how to get PNG from that. If you want to process a whole bunch of files at one time, which if you are making a movie, you're going to have a whole bunch of frames. Okay, so each magnetization state, you push it through here. You are going with a wildcard. And you can use just your standard shell globbing. That's frequently enough. But there are some fine controls here that you can use to select more finely. These are actually regular expressions, if you know what regular expressions are. Okay, so let's go ahead and do one here. So the F flag, force overwrite of output files. If you don't put this on and you write out to some, this program will create the output file names by taking the input file name and just changing the extension. If it finds out that there's already a file with that name, then it will, instead of overwriting it, will tag on -0001, -0002, that sort of stuff. So, but if you want to overwrite it, which frequently you do, if you're sure, you put -F in. You specify the configuration file that you want to use, which in this case was otprob1_2.config. What's next? The files that I want to convert. So otprob12. What do I got here? Striking out here. What is it called? Stage. Why did that come up? There we go. Okay, so that's a file I'm going to convert. And okay, so a little bit of magic here. I want to get PNG files because they're smaller, they're compressed. So I'm going to send it, I'm going to create a pipeline. I'm going to send it into another program to do the conversion. And that particular program is called whatever you have on your system. But ANE to PPM is one that ships with OOMMF. That can convert to PNG format. I think that's all I need actually. And then I want the output extension, the substitution on the output, I want it to be .png instead of ppm or whatever. So let's run that and see if that works. Okay, looks good. All right, so here is showing you what it did. I took this file, I ran it through this filter program, and then output this file. So if I, for example, open that up, PNG, here it comes up, and there it is, and it tells you what the size of it is, and that's what it looks like. Okay. If I specified, if I put a star here, for example, then I'll get all the files that are there. Okay, so in this case, currently there are 2 here, so it goes to 2 of them. Okay, and so that's how you get images. Okay, I'm going to take a question that goes back earlier to AVF to ODT conversion. When we take averages along the line y-axis, can we fix the z-axis value? Yes, you can select the z-axis by using the region command. So the region option. So if you go -region, and I'll give an example of this in a moment, you can select a rectangular box that you want to work on. And so if that box you select has only one layer of z, then all the averaging will be just in that layer. So each line will just be in that layer. So another question about measuring fields. Anything that comes out as a separate output in OXS, any of the field outputs, you can work with any of them. You can output any of them to a file and work on them as needed. But that's the level that you can work at. Whatever output you see, if you open up Oxy and you see the output list, that's what you can work on. If it's not in there, then there's no direct support for it. Although some are starting to do this now a little bit more because there's so many outputs. Some of the OXS EXT objects have optional outputs. So recheck the documentation. There may be additional options, maybe additional outputs available if you select them in the MIF file. Okay, so the next step now, you know how to create an image, right? So suppose we want to make a movie, okay? So to create a movie, you basically, okay, I'm just going to go to the slide deck. I don't want to spend too much time on this. Okay, so you can use AVF to PPM to convert all your files at one time, for example. Okay, and so I did this, for example, with the output from the problem that we did, the homework problem, and I created a whole bunch of files named 00 PNG, 01, 02, 03. And there's this little, I didn't go over it here, but I did some fancy stuff with the pattern expression to typically, if you look at the output file names that you get from MMArchive, they have a stage number and they also have an iteration count. So this is a great big long name. And I'm going to feed it into a program called FFmpeg to take all my images and make a movie out of them. And it will read a whole bunch of files at one time, but it gets confused if there's multiple things which are multiple numbers. And so I use the this outplatexp to drop the iteration number. So I just got the stage number because that's what I'm keying off as a stage number. There are other tools you can use to rename batches of files, but that's one way to do it. Okay, so once I have this complete list, then FFmpeg is, there's lots of tools. Once you have a bunch of images to create a movie, one particular free tool is FFmpeg, and here I have a movie page actually on OOMMF, which I go in a little bit more detail on this. But you basically, here are the input files, all the files you want to use. That's the -I. These are going to be incremented by steps one at a time, starting with 0. So it goes 0, 1, 2, 3. That's how this comes in. This leading R, this is the frame rate for the input files. So this controls how long the simulation basically pauses on each frame, or spends on each time, the dwell time, the inverse of the dwell time. So this basically, this will control how long the simulation runs for. So 4 seconds was the one that I gave you, for example. This selects the codec, right? So this is what H.264, it's a common one. But there's a long list of codecs that are in this package, so you can take a look. These are quality factors. The bigger you make these, the higher quality the output is, but also the bigger the output. The R here at the end is the output frame rate. -AN means no audio. A is audio, N is no audio. And then this is the name of the output file, okay? I'm not, you just do this, it goes really quick actually for these sorts of things. Okay, all right, so let's look at the dispersion study. So this is based on a paper published in 2013 in Transmag, Venkat and et al. And so they look at this particular sample. It's a micron long, 50 nanometers wide, 1 nanometer thick. They gridded it up into, I think, 2 nanometer cells in plane, 1 nanometer out of plane, so it's just 1 layer thick. And they want to apply they start in a relaxed condition, so they magnetize it along the long axis, the x-axis, and they relax and they use that as the initial state, and then they apply a field. And the field they apply, this is the temporal signature, so it's a sync pulse. There, sync omega t, where omega is picked based on the frequencies that we're interested in looking at. It's offset from 0. So at time 0, basically there's no pulse, and then it peaks at 50 picoseconds, and it comes back down again, all right? And I showed you this, how you set up the sync before. This is using the transform Zeeman class, which allows you to have both a time variation and a spatial variation, okay? And so for the spatial variation, they also chose a sync function, okay? Sync in X and sync in Y, and that looks like this, okay? And that's centered actually in the middle of this part. And so at time 0, it's 0, but then as time goes on, you get this pulse, it's strongest in the center, and it's multiply, right? So that then allows you to excite certain frequencies, and you can take a look at those in transform space. Okay. So here are the steps to go through to visualize that in transform space. So the first thing is you run the simulation and you collect the full magnetization at a regular sequence of steps in time, okay? If you look in the sample files, there's a file called Dispersion.mif. If you run it without any parameters, you'll get the simulation that I'm showing now. There are a bunch of parameters to control what type of waves you are exciting, symmetric and asymmetric, all this business, okay? Refer to the paper for details, but you can use this file. I think it supports all the different modalities that they talk about in that paper. Once you have that large collection of files, you use AVF to ODT, okay? This I think came up in one of the questions I answered, to extract the Y component of the magnetization along the center line only. So we're going to collect here magnetization just along the center, okay? This particular example, it's set up, the spin waves are propagating along the x-axis, and we want to look at, we're just interested in the center. We don't, not curious. We don't want it to get involved in the edge modes. So this is just in the center, okay? And you can do that with this AVF to ODT command, which I'll show you. And then this will produce a single output file, which will have one column with 500 by 5,000 values. So let's step through that. Well, let's try to. Let's see here. Okay, so I need to go to, what's the name of that directory? There's a lot of files and I stuck in the directory. Okay, Dispersion OOMMFs. Okay, so here are all my OOMMF files. Okay, there's a lot of them. There's 5,000 of them. So I do AVF to OVF. Oops, wrong page. Yep, okay. Okay, so I don't want to do any averaging. I want the point values. So for my average type, I suggest I select point. And the only output I want is the MY component. So I turn off all the default outputs. So default position 0, default values 0. I don't want any headers because I'm going to be bringing this into Python. I just want the bare data. I know what the sizes are. Okay, so I'm using the valfunc command here. The first thing is the label, which doesn't matter in this case because there aren't any headers. The units, that would be, if I had headers, the units would be in that column. And then the actual value, which is VY. There's VX, VY, and VZ, and some other things are available. VY is the Y value in the file, in the data file, which in this case is MY. Okay, region. Okay, I don't want the entire file. I just want that stripped down the middle. So you specify in the region, you specify the minimum XYZ and the maximum XYZ. If you put a dash in, then you get the minimum or the maximum X value, minimum, and so on. So let me just write this down because then it's fairly clear. So this is my region select. So this is going to be, that dash means the minimum X value in the simulation. So that's going to be the left-hand side. This dash is a maximum X value. So it's going to be the right-hand side. This corresponds to the Z coordinate. So the minimum Z and the maximum Z. In this case, there's only one Z value, so it doesn't matter. This is the Y coordinate range. The strip is 25 nanometers wide. I want the center, so 25 is in the middle. The cell size is 2 nanometers. So if I go from 24 to 26, I'll get that middle piece. You can actually make this a bit smaller, but if you make it too small, you might have some problems with rounding errors. Make it too big, you're going to get the cell next to it, okay? But anyway, that selects a strip right through the middle. And I'm going to be writing out MY there. And okay, the files that I want to use, which are these guys. So dispersion, oh, wait a minute. That's supposed to be a quote, okay. So dispersion, and I want to do them all. Well, actually, let's just do one first and see what that looks like. And okay, so I'm going to, I think this is the syntax. Let me see here. Yeah. Oops, I screwed up something here. Let me look at the error message a little bit better here. Yeah, I'm not paying attention. Okay, Sorry about that. Unknown option. Yeah, that's supposed to be, sorry, wrong command. AVF to ODT. How about that? Does that work better? There we go. Okay, so there's no headers because I specified no headers. And there are going to be 500 values here because there are 500 cells along the x-axis. And this is the MY component. This is the MY component starting from the left and going to the right. Okay? So what I'm going to do now, though, is I'm going to, sorry, I have to move so I can see behind the Zoom stuff. I want to process all the files. Okay? So I'm going to do that. I'm going to do that. So that selects all of these files in this directory. And I'm going to send them to a particular file. Let's call it foo.dat. And I'm going to truncate just in case I already have a foo.dat there so I don't append it to it. And let's see what happens when I run here. Okay, and it starts running. Okay, so it takes each file. You can see here the stage number is incrementing, and it's pulling out that one line, and it's appending it to this file, foo.dat. Okay, this takes a little while because there's a lot of files here. I'm at 1,000. I'm going to go ahead and stop it now because I already ran this. But you let it go, and it goes all the way up to 5,000, and you end up with this big file that has 500 times 5,000 values in it. Okay, and so I did that previously. It is here. Okay, and there's all the files. There's all the values. Okay, so it's a big file. So now the next step, let's go back here. So that's now, so now you know we have foo.dat. It's got that many MY values, no header, no trailer. Okay, so the next step then is I'm going to load it into Python. Okay, so let's step through that and show you what that looks like. So I have a Python shell somewhere. There we go. Oh, okay, I didn't load it up, so we'll start that. Okay, so first I'm going to import, of course, import XMP. Let me go ahead and import a couple other libraries I'm going to be using. So we'll use matplotlib for displaying the dispersion curves. And the next example I'm going to show, I'm going to use MyOVI. Put that now. Just a second, let me check here. Yeah, okay. I'm going to go ahead and import that now too. Okay, so I'm ready. All right, so once I have my libraries loaded, now the first step is I've got this data file. It's got 500 by 5,000 values all in a single column. So I'm going to read that. I'm going to store it into a vector called A using the load text command. Okay, those are in text format. And so I just have to import the data like that. Okay, it reads it in, stores it in A, and dun, 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 dun. Come on. Really, this works. There we go. Okay, so if I look at A, it's this one long vector, right? Now I need to do a 2D FFT. I need to convert that into a matrix. So I'm going to use the reshape command in NP. I take A and I'm going to reshape it. And I know that my data has 500. It's 500 across each row. So I just do that. And so now if you look at, I can type, you see now it's a matrix. It's 5,000 by 500. Okay. Now before I take the FFT, I want to subtract the remnant state, right, which is the first row. So I'm going to set B equal to, subtract off a 0. Okay, so I'm going to subtract off the first row from everything. Okay, so now if you look at, for example, Does that work? So the first row of B is all zeros. If I look at the second row, there are values there, okay? So now I have B, B is the same shape as A, okay? But I subtracted that off. And so now I just take the f of t, 2d f of t of that, okay? And as long as you don't have a prime dimension in there, that's pretty fast. And now I'm ready to display it. So let's see if I can type out properly here. I'm going to scale logarithmically to see it better. And I'm going to plot the magnitude squared and f of t shift that just centers the frequencies. There's a square and aspect auto. And I dropped something somewhere. Let's see, 1, 2, what am I missing here? One, two, I got too many here. No? Sorry. Oh, I know what the problem is. This is supposed to be a dot. Duh. Still not good. All right, we're getting closer. How about that? There we go. All right, sorry. And now we can show. Okay. Hazards of live TV. All right, so there's that. Let me make it a little bit bigger so you can see. Okay. I think if I change the, not this one, color map, it'll be a little bit easier to see. There you go. Okay, so there are the dispersion curves. This is the frequency, this is 500, this is the spatial frequency, right, along X, and this is the temporal frequency, okay? So that's how you can get these curves. And for more details, see that paper I referenced earlier, okay? Okay, I think we're okay on time. Let's see here. Let me go back to the slide deck. And if you look in the slide deck, there's that image again, okay? Okay, another question that came up is 3D quiver plots. Again, you've used basically the same sort of techniques. This time I'm going to use YIVI to do the display. For this particular example, I'm going to take an OOMMF file that I got from standard problem number 3, which is a cube, and it's the cube is sized so that you get a vortex inside in the equilibrium state. So the first thing is you want to take that OOMMF file, and I'm going to use AVF to OVF with an irregular grid, so that I'll get an output which has got 6 columns. It has X, Y, Z, MX, MY, MZ. And that then is going to be fed into Quiver 3D. So let's step through that. Okay, so check my notes here. Okay, so the first step is AVF to OVF. Let's look at the help here. Okay. Oh, one thing also I just sort of mentioned here. The info option to AVF to OVF tells you about the file that you feed it. So if I feed it an OOMMF file here and I say info, rather than doing any conversion, it just opens up the file, looks into it, tells you the dimensions, the size, the range of the values. Tells you here the cell size, the mesh size, and so on. One thing is I'm going to be showing this in a 3D visualization. If you try to draw that many arrows, it's too cluttered. You can't see very much, and it's easy enough to you can use AVF to OVF to subsample. So there's a subsample option. Okay. There's also, in addition to subsample, there is also a resample option where you can choose a different grid and have interpolation between the points. That's also an option in AVF to OVF. Yeah, okay, let's just go with that. So that's the program I'm going to use. That's a file I'm going to load in. Okay, there's, like I said, there's too many points, so I'm going to subsample every 4th one in each dimension. So that's 4 times 4, 1/64th of the data, right? I want the output format to be text as opposed to binary, so I can read it into Python easily. I want the grid to be a regular grid, because that's what that's the easiest thing to feed into Quiver 3D. Oh, I need to get rid of the. It's easy if I get rid of the pound. Let's just look at that first off. Does that work? Yeah, okay. So let's just look at that output, okay? So it's a regular mesh, so that means that if I look at this thing, I've got, it's text, I've got 6 values here. So this is the X, Y, Z coordinate, and then the MX, MY, MZ values, okay? I'm gonna get rid of the header lines here, and also the trailer. So I'm gonna feed that through grep. V means everything that doesn't match, and head is the beginning of the line and the star. All right, so let's look at that. Type right. No, I did not. Okay, less. No, get the key there. Okay, so now that's the beginning of the file. That's the end of the file. There's no headers. It's just raw data, 6 values, right? Okay, so I can output that into my file. Let's call that bar.dat. And what I screw up here, sorry. Yep. Yep. I just need to get rid of that. Okay, there we go. So now I have this file bar.dat, and you can see it's just the raw data. Okay, so now I go back to my Python shell, and I'm going to read that data in. Okay, so I'm going to reuse A now. A is np, just like before, load text. The file now is bar.dat. Bar.dat. Okay, this one reads a lot quicker. It's a much smaller file now. Now the thing is that Quiver 3D, the program, the routine I'm going to use, it wants 6 vectors, 6 single vectors. If I look at the shape that I have in A, it's 512, because this is a 8 by 8 by 8, is that right? Array. For X, Y, Z, MX, and Y, and Z, I want to break those out. So I can do that just like this, using the H-split routine. I feed it A, and there are 6 columns. Okay, so if I look at, for example, that, each one of these is now a vector of length 512. Okay, and okay, the other thing is that if you remember, the positions are in meters, and this is a micromagnetics thing, so they're 10 to the minus 9th meters. And so it's helpful to actually go ahead and rescale the positions. So I'm going to multiply each of the position vectors by 10 to the 9th, so that they're now in nanometers, just for convenience. It makes the scaling a little bit easier. Okay, and now I've already imported Maya VI, so I just have to run the Quiver command in lab.quiver 3D. Okay, I feed it X, Y, Z, MX, MY, MZ. Okay, you select what the glyphs are going to be. You can use arrows here if you want. I think for this particular one, cones look better, so that's what I'm going to use. Your choice. And I'm going to color in a moment using X, using the X coordinate. Okay, and it comes up, and you get that sort of a thing. And hang on, let me color it now, make it a little easier to see. Color mode equals color by scalar. If I can get to it. There you go. All right, there we go. right? And you can grab this, move this around, right? And throw some axes up here if you want to see what the axes are. And that's what you got, okay? So, any questions here? Okay, question. Is there a way to write magnetization data of a region using MMArchive instead of writing magnetization data of complete simulation data? No, there is not. Should there be? I don't know, maybe there should be, but it's not. Okay, AVF to ODT, can we take the average along any arbitrary direction for a 3D sample? Again, no, it only supports along coordinate axes. If you want to do something like that, then you would have to write your own code to do that, involving some interpolation. Although you can use AVF to OVF to maybe to help you with interpolation, I'm not sure. But at any rate, the file format for the OVF files, it's very simple. It's fully described in the documentation. So if you need to work with the raw data to do your own programming, use that as a reference. Okay, I think I'm almost done here. Let me just pull up here. Okay, so here are just the steps that I did online on the terminal there live. You can follow that if you want. And the data file that I use is standard prob 3 vortex OOMMF. It's in the example files, the sample files that I gave you. Okay. One last thing I wanted to touch on is here's another type of visualization that was pioneered by Bob McMichael in this paper that he wrote with Mark Stiles in 2005. They took a small nano element, and then they hit it with a spatially varying pulse, and they looked at the average magnetization in transform space, okay, in the Fourier transform, and you get the graph that looks like this. If you look at the average magnetization, and so you can see that there are peaks, okay, and which peaks you get, it depends upon what the excitation was, right? So they varied the excitation to excite different modes. But then the question is, well, I have this peak here. What's going on at that mode? So what they did is they collected all the magnetization states at fixed periods, just like we did before. But then they said, okay, well, what's going on at 4 gigahertz? So they took all these images and they pulled out a pixel, each pixel. And if you look at all the images and you pull out a single pixel across all the images, then you have what that one pixel is doing, that one spin is doing over time. And so they took the transform of that, they took a 1D Fourier transform of that, and they looked at the magnitude for the response at that pixel at, say, 4 gigahertz, okay? They did that for all the cells, and you get this color map. So if it's light here, if it's white, then that means that that pixel has a strong response at 4 gigahertz. If it's dark, it has a weak response. And so this allows you then to image what the mode is like at 4 gigahertz. And so you can see for this particular example, it's an edge mode where the two ends are where you have movement, okay? And so then they're able to identify each of the different peaks. They can identify what the mode is for the different peaks, okay? So I think this is really beautiful work. And if you want to know more about it, you should annoy Bob McMichael. There's another paper that he and I wrote together where we show how you can use this technique for a micromagnetic problem, which is published here. So that's the conclusion. I actually finished a couple minutes early today. So I'll take a few questions maybe. So just some references for Python. Ask the UberMag people about Python. They know a lot more about that than I do. Okay, can I simulate spin, orbit, torque, induced magnetization dynamics in OOMMF? Can I independently simulate field-like torque and damping-like torque? And there's also a question about modified exchange energies. One of the things I had hoped to do in this series, but I ran out of time, was to show you how to write an extension to do spin orbit torque, also bulk DMI, and maybe some other stuff. So if there is interest, we can continue this discussion on NanoHub. I will post some hints on how to create this extension, and we can work through the extension for SOT, for example. If that sounds good. So I don't know. Does that sound good? People interested in that or not? Are we done? You want to do a poll, somebody? Anything else? Okay, I think that's all we got right now.
So we can ask how many people are interested in writing an extension, well, let's first ask how many of you are interested in learning on how to write an extension. So you can use a yes or no buttons in the participants panel. So if you're interested,
and if there's interest, yeah, if there's interest, we can discuss different types of extensions. Whatever people are interested in, if it's doable.
Okay, so everyone, please click either yes or no. So it looks like there's some interest. So 21 answered yes, 5 answered no.
Okay.
And
how many no?
Coming up. So it seems like it's interesting.
Okay. Yeah, it's okay. So I'll post some stuff there over the next couple of days, and we'll get started, and we'll see how it goes. All right.
Okay, very good. So are you done, Mike?
I am done. I have another meeting in 2 minutes, so I have to dash.
Well, let's thank Dr. Donahue. Thank you so much.
Thank the audience. This has been a long road to hoe here. So
yeah, it's a
thank everyone who's involved. Thank you.
So you can use the clap button in the reactions panel to thank the instructor. And with further questions, please go to NanoHub. There is a team of experts available to answer them. And then I hope Dr. Donahue will provide some guidance about writing an extension. It's possible that later we'll record an additional session with answers to questions if there are important questions that need to be answered with demonstrations. Otherwise, thank you all for participating.